So this video is intended to help you understand how to do error analysis in the H/E lab in modern physics, and also how to do error analysis anytime you are doing a linear fit. So I don't want to explain the physics of that lab, I just want to explain the process of error analysis. In that lab, you make measurements of stopping potential at different frequencies, and so I have some data that I stole from a lab group of their measured stopping potential right here and the associated frequencies, and there's a linear relationship which we can see fairly quickly by doing a plot of frequency along the x-axis and stopping potential along the vertical axis. Sure enough, there's a linear fit, or there's it looks like a linear line. So I'm using LibreOffice, a free spreadsheet program, but the same stuff works in Excel. You can insert a trend line. The formatting here is terrible, but it gives you a slope, and the physics that we're interested in is associated with that slope. But we want an error in that slope, and there's no simple way to get the error plotted on the graph. And I want to show you in this video how to get the error in that slope. So it's from a technical point of view a little bit of a pain. It works like so. You need to select several cells, an array, a 2x5 array, and after selecting that you have to type equals LINEST parentheses and then select the y values, so the stopping potential, comma, the x values, in this case the frequency, comma, true, comma, true, end parentheses, and then Control Shift Enter. And that produces a whole bunch of statistics. What I care about right now are these two cells. The top cell here, 4.27 times 10 to the minus 15, represents the slope. Sure enough, it's the same number over here. And then the second cell is the error in that slope. Now that error makes to determine that error statistically requires making some assumptions about your data. It makes two main assumptions. The first is that the data, that your measurements are sampling from a relationship that is linear, which we kind of sort of already made that assumption. The second assumption is that the errors, the deviations of your measurements are all random from that linear relationship. That is, there's no systematic process pushing all your measurements to a higher value or a lower value, or skewing it in some way beyond random deviations from that linear relationship. And by making that assumption of making those two assumptions, it's able then to go through the statistical analysis to determine what the implied error in the slope is. In this lab, Planck's constant is equal to this slope times the charge of an electron, so 1.6 times 10 to the minus 19, and sure enough that's pretty close. Now if you want to do error in the Planck's constant, then you have to take the error in your slope times 1.6 times 10 to the minus 19, and sure enough Planck's actual constant, which is 6.626 times 10 to the minus 34, lies within these errors. And so this is consistent with what we know about Planck's constant. So it's only if usually the error analysis in modern physics labs can be done using the partial derivative method that you learned in general physics. However, this is a lab where you need to do the slope, and so the error analysis by necessity is different. And in other physics labs, sometimes the physics of interest is through using slope, and in that case you should always do this sort of analysis, where usually with a spreadsheet you do a linear fit and then get the slope and the error in that slope through this process. If you have any questions about how to do this process, or Excel isn't behaving for you the way that that this spreadsheet behaved for me, feel free to ask me a question. Good luck.